Good morning, good afternoon, or good evening, depending on where you're listening to this Doble webinar today. It's our great pleasure to have you here with us. My name is Simon Sutton. I'm the Director of Services for the new Doble/Altanova group, and I'm going to be your host today. I'm here with my colleague Stefan Dragostinov. I apologize, Stefan. I don't know what happened there. It's been a long morning. Stefan is going to be our speaker today and talking about factory inspections and FAT, which follows on from the webinar we did last month, and Stefan will mention a little bit about the things that were covered last month as well. The webinar is going to run for approximately an hour, after which we'll handle questions at the end. To put in your questions, please use the questions tab on the right-hand side of your screen there in the little GoToWebinar control panel. We'll handle all the questions at the end, and if you click the little box, the little square box with the arrow pointing out, that will undock the questions tab. You can drag it to another part of your screen. It also makes it bigger, which just makes it easier to type your questions into. So with that, let me introduce Stefan. Stefan graduated from Sofia University in Bulgaria in 2008 with a master's in electrical power engineering. After that, he worked for Hyundai Power Transformers in Sofia as part of their high voltage laboratory team. He's been with Doble since 2014, and he's responsible for the assessment of transformers, including online and offline condition assessment, factory inspections, and work test witnessing. He's also actively involved in CGRE, including CGRE Working Group A263, which is on transformer impulse testing. So Stefan, over to you, and we look forward to the webinar.
Thank you, Simon. Thank you for the introduction, and thank you everybody which decided to watch our webinar today. The topic of this webinar will be the importance of factory witnessing, routine testing, and FAT. First of all, just to say some words about Doble for those who are not familiar with us. Our mission is to ensure that all people have reliable, safe, and secure energy by providing advanced diagnostic and engineering expertise for the energy industry. This is the timeline of Doble. It was established in 1920. Last year we have a 100-year anniversary, and throughout the time we grown a lot. In 2003, Doble Power Test began operation as part of Doble family. In the recent years, few companies joined Doble, including Morgan Schaefer company with their first-class DJ products, Vanguard, and Manta Test Systems. Most recently, Doble acquired Altanova and Phoenix Technology. Altanova Group contains ESA, which is known with their test instruments, and Techimp, famous in the partial discharge field. We not only produce test instruments, but we provide complete package of technical services, including condition assessment and testing, laboratory testing, and forensic investigations. We also provide trainings, conferences, in-house courses all around the world, and things like this webinar, of course. Today, I will be presenting you a companion webinar on transformer procurement process. My colleague Simon Ryder went through the first part of the procurement process in his presentation in November. including identification of the functional requirements, how to prepare a specification, selecting a good supplier, managing projects, and design review process. In this second half, I will speak more about inspections during manufacturing and also factory acceptance testing. I will also go to use some examples and case studies for issues we found in the manufacturing process, as well as field testing. What is the reason to perform inspections during manufacturing? So the inspection during manufacturing gives you the opportunity to check the active part of the transformer, including what materials are used, their quality, and if they comply with what has been agreed on a design review stage. We can check what the build quality is and ask for correction, as well as we can check for issues related with cleanliness. We can check if the manufacturing progress agree with the proposed schedule as well. Progress inspections are usually planned at the design review stage based on quality plan and manufacturing program. Usually we suggest as a minimum inspection on the active part before dry out and witnessing the work tests. While before dry out, it will be no rush at that time, and usually it will be enough time available to conduct the inspection and all the checks needed, and also correction to be done if necessary. In case of a critical unit, or if we have concern about the manufacturing quality, we usually suggest inspections once the individual windings and core are ready, and one additional inspection after dry out. In some specific cases, additional inspections may be needed. So how the progress inspection looks like? First of all, this is what we would normally expect to see during the inspections. We have the core and winding assembly completed to certain stage before dry out, in this case on the screen, already prepared for the inspection without somebody working on the active part, and all tools and materials cleared out. Some things we check during the progress inspection includes the working area. Is it clean, tidy? This is sometimes underestimated by the manufacturers, but you cannot expect dirty, messy area and at the same time active part which is clean with no contaminations. We expect all the components, materials, as well as core and winding assembly to be clearly identified. The drawings for the unit we inspect and the documentation required to be available, and for the correct transformer. We also check the quality checklists if they are completed and filled correctly, including NCRs issued during assembly. We would like to see if the materials and components are stored correctly also. During inspections, we don't expect to have tools or materials left on the core and winding assembly. They could be easily forgotten there and cause significant damage during testing, or even worse if these damages happened in service. Some manufacturers block the openings of the core and winding assembly using simple methods like crushed paper in order to avoid contaminations to be trapped. We check the core and especially the top yoke for gaps between the laminations, damages on the laminations, as well as the core for typical places where you can find damages. These are the tips. Also, we check for wave visible if the core blocks are correctly aligned. We also check the core bolts or straps if they are tightened correctly and marked. The correct grounding of the core frame is very important in order to avoid issues during service, and because of this we check if the core ground straps are inserted correctly. The cooling ducts or different sections of the core should be bridged accordingly. The checks we do on the windings includes examination of the conductor or other visible insulation for damages, uncontrolled use of glue, and also for dirty marks and other contaminations which can compromise the properties of the dielectric materials or clearances. Another important point is the winding and blocking alignment, because it is critical for the short circuit stability of the winding. Another area to look is the lead assembly. If the tap leads are labeled correctly, we have seen issues in the past with leads which are not labeled or incorrectly labeled and then connected in the wrong way to the tap changer. Such problems are easily caught by electrical tests like transformer ratio, which is usually part of these progress inspections. We check if the support structure is robust enough, and the leads are also checked for physical damages, uncontrolled use of glue, dirty marks, or any other contaminations. Bolted connections are critical items, so we check if they are tightened correctly and marked accordingly. On the lead assembly, we check if the clearances between the leads are sufficient, so we don't have accidental short circuit between leads or discharge activity. Some fasteners are filled with dome caps, especially those close to leads and on the tap changer. We check this as well. Going to the tap changer, we check if it is correctly supported and if the tap leads are not excessively tight. This could cause deformation in the selector geometry and damages or even a failure during operation. The manufacturers perform electrical measurements during assembly. The purpose is to check if all the connections are made correctly and all leads are connected to the correct place or to the correct terminal. The test which we consider useful at that stage includes transformer turn ratio, winding resistance, core frame insulation resistance, and maybe CT check if we have current transformers already mounted.
So just to say, I can see we have some people who've joined since the beginning of the webinar. So just to let people know, the webinar is going to run for approximately an hour. We'll handle all the questions at the end. We've already had a few questions come in. You can put your question in the question tab on the right-hand side of your screen in the GoToWebinar control panel. If you click the little box with the arrow pointing out from inside it, that will undock the questions tab and you can pull it off to a different screen. Makes it bigger, just makes it easier to use. Also to say, somebody's asked about will the presentation be available. We won't make the presentation available, but everybody who's listening will get a link to the recording, so you can always listen back afterwards as well. So Stefan, back over to you.
Thank you, Simon. So I will now show you some examples from our practical experience during manufacturing inspections. On that picture, you can see an active part ready to get into the oven, but we found between the top winding and top yoke some tools left. Also a glue stain. The problem with the glue is that during drying, it sucks moisture from the atmosphere, and we don't need this moisture in on the active part. Practically, it can cause discharge activity or even worse if it's a breakdown. Another problem, misaligned winding and blocking. As I already told in the previous slides, this is important for the short circuit stability of the winding. Debris on the core blocking. Yeah, this is another issue. They could easily be spread all around the active part with the oil flow when this unit is filled with oil. So we would like to have the unit perfectly clean before tanking. On that picture, we have some damages on the tap lead, insulation, which is another issue, and it's something we don't like to see on a new transformer, and it can cause a problem during service, during testing as well. And what we can check also is the progress, the manufacturing progress. In that picture, we have the transformer ready for inspection, but with tap changer missing. In this situation in particular, we have a delay of a few days or few weeks practically, because the manufacturer had a problem with the supply of the tap changer. I mentioned that during progress inspections, many manufacturers perform testing, and on this diagram you can see measurement, the results measured during transformer ratio, and the graph is quite unusual because of a problem related with the tap changer. In this situation, the problem was identified at a very early stage, and there was enough time to send back the tap changer and replace it by a new one in order to prevent further delay in the production, testing, and delivery of the transformer. FATs are performed once the construction process is complete, the active part is positioned into the tank, and the purpose is to reveal any design and manufacturing defects and to verify the materials used. It is the first time we can see the unit assembled and check the functionality of the auxiliary equipment. From customer point of view, it is faster and much cost-effective to rectify any errors at the factory rather than on site. The work tests will ensure the transformer comply with our expectations and if it meets the guaranteed limits. In addition, FATs provides valuable reference data for subsequent condition assessment testing in service and after commissioning. Usually, factory acceptance tests are witnessed by an inspector, not only to verify that all the tests scheduled are conducted, but also to perform the last quality assurance check. The manufacturer should demonstrate the unit is acceptable for service and comply with customers' technical specification. The inspector needs to determine if the manufacturer performed the tests correctly, which is very important, according to specification and applicable standards, using appropriate measurement techniques and suitable calibrated equipment. Generally speaking, we want a unit built to meet our spec without having performance issue in service. So the final proof is in form of factory testing. These tests are sometimes viewed as a routine, which may cause utilities to miss the opportunity to identify and correct any issues in the factory. I already mentioned that applicable standards should be used, and IEC 60076 Part 1 is the standard for power transformers, where you can find the minimum requirements for routine and type tests. This standard includes method for some of the performance tests, and some of the other tests have their own standards. We can classify the tests in various ways, but the most basic one is, let's say, routine, type, and special tests. The routine tests are performed on every single unit. Type tests, they are to prove the design and performed on one unit. Usually this is the first unit if we have a series of few, and they vary based on the voltage class of the unit. Special tests, these are a group of tests excluded, which are performed in addition to the routine and type tests, and agreed between the manufacturer and purchaser. This is a list of tests we need to perform during factory testing. It includes performance tests like no load loss and impedance, temperature rise test, sound level measurement. Also, it includes dielectric tests like lighting and switching impulse, applied voltage, induced voltage test, and so some of the tests have their own standards, and that's the case with temperature rise test, which along with specification of cooling and temperature rise are described in another standard, which is IEC 76 Part 2. It covers the test at rated power, and if we need to perform the test at some mode or power mode beyond the rated one, or let's say dynamic temperature rise, we should refer to the loading guide, which is a separate standard, IEC 76 Part 7. The situation with the dielectric test is a little bit more complex. The general definitions and test methods are explained in IEC 60060 Part 1, but this standard is common for all kinds of equipment. On the other hand, the dielectric tests include isolation level and external clearances for power transformers in particular. They have their own standard, which is IEC 76 Part 3. Another example for test with a specific standard is sound level measurement. The test is explained in IEC 76 Part 10, including requirements to the measuring equipment, test procedure, and how to calculate the final results. However, something you won't find in this standard is some specific limits for sound level, and these should be specified by the customer at the beginning of the procurement process. Another family of standards which could be applied for power transformers are IEEE standards. It has some more different approach to in comparison with IEC and all requirements for the test, they are listed in common document, which is IEEE C571200. And there is only one more companion standard to this one, IEEE C571219, where you can find the method for performing the tests. I cannot say that both standards, IEC and IEEE, are very different, but they differ in some specific areas. It is always preferable, and we advise our clients to insist the manufacturer to provide detailed test plan for the factory testing. This is an additional document to the quality plan, where you can find details for the work tests, including the test method used, also measuring equipment, and what the expected result is. In case of a limit, what the limit is. The detailed test plan should also indicate the acceptance criteria, and in case we are not happy with the methodology or the equipment used, we can discuss this well in advance of the factory testing and not lose time in the test laboratory. When we witness factory testing, there are a few things we already want to check. This is test equipment, and particularly if it is within calibration and if it is suitable for the particular test. We also check the test connection, if it's correctly prepared, and some measuring equipment insists correction factors like power analyzers. They need measuring transformer ratio to show us the actual result. We check this if it's correctly, if the correct ratio are applied in the instrument. We insist also raw measurement data from the manufacturer in order to double check manufacturer calculations. For this presentation, we will be focusing on some of the performance tests, like no load loss and impedance, load loss and no load loss and current, load loss and impedance, and temperature rise test. The results for this test are very frequently guaranteed values. We will also speak about some dielectric tests, like lighting impulse, switching impulse, applied voltage, and induced voltage test.
Just a quick reminder to put your questions in using the questions tab in the little control panel on the right-hand side of your screen. Sorry, Stefan, back to you.
Thank you, Simon. Transformer load loss and impedance is the first test which we will review. It's a routine test as per IEC 76 part 1, and it is defined in item 11.4 of the standard. The purpose of the test is to verify the load loss and impedance if they agree with the guaranteed and expected results. The results are important not just to capitalization of the losses, but also for the safe operation of the unit. Comparison with calculated values gives us an indication about the design and build quality, and also about eddy losses due to the leakage flux in steel parts. In addition, it is important to know impedance and load loss to carry out temperature rise test as well. How the test is performed, usually by short-circuiting one of the windings. It's more convenient to do this on the LV side and supply the other winding from the test source. The supply is usually on the high voltage side. So I will move to the next slide where you can see the test circuit diagram. This is a simplified diagram representing load loss and impedance measurement on a single phase transformer for simplicity. We have the test object in the red square with the low voltage winding shorted and high voltage applied from the test source. The measurement of voltage and current are performed via measuring transformers and power analyzer. The power analyzer combines voltmeter, ammeter, and wattmeter just in one instrument. All the modern laboratories used power analyzers instead of a single meters. The source is represented by a generator and suitable test transformer. The supplied current should be equal to the relevant rated current or at least 50% of the rated current. Load loss result they are corrected to reference temperature, and this is 75 degrees as per procedure outlined in IEC 76 part 1. It is important to measure the transformer temperature during this test correctly. Otherwise, the result will contain significant error. IEC recommend to do so after the unit has been filled with oil and without excitation for at least 3 hours. And the difference between the top and bottom temperature is less than 5 kelvins. To obtain this result more rapidly, the liquid might be circulated by a pump if the transformer is, let's say, equipped with pumps, and the reference temperature is the average of the top and the bottom liquid temperature. The measurement should be performed quickly so the temperature rises do not cause significant error. In case the unit has more than 2 windings, the load loss measurement is performed between each pair of the windings. In case of 3 windings transformer, we have 3 combinations. The results are then recalculated to allocate impedance and losses to individual windings. In transformer with tapped windings exceeding variation of 5%, the test is performed on principal and boxed extreme tap position. This is important for parallel operation of the transformer. Measurement of different tap position could be specified in the inquiry, and especially in case of asymmetrical tap range, the measurement of losses could be done on the middle tap position. As I already noted, the result should agree with the values expected from the design review, as well with results from sister unit if we have previous measurement. It should also respect the guaranteed values. IEC allows some tolerance for load loss and impedance as well, the total loss, but many users specify their own limits, and if they are exceeded, then penalties apply. No load loss and current is another performance test. Details for no load loss measurement are listed in IEC 76 part 1 item 11.5. The purpose of the test is to verify the no load loss if they agree with the limit guaranteed and with the design values. Also, results gives indication for design and build quality of the unit. The test is important as no load loss are presented once the unit is energized, and the result is used for temperature rise test. So, how we perform this test? We have one winding which is energized from the supply, and the other windings which are left open. The measurement is performed using measuring transformer and power analyzers similarly to the load loss and impedance. For convenience, the supply is usually applied on the low voltage winding in the test field. Specific for this no load loss measurement is that the voltage on the unit under test is usually distorted, caused by non-sinusoidal no load current of the test object, and both RMS and mean voltage should be measured. We can declare that the no load loss measurement is valid if the difference between RMS and mean voltage is less than 3%. To obtain a final test result, the measured no load loss are corrected using the formula which you can see at the bottom of the slide. It is very simple and very well defined in IEC 76 part 1. During no load test, the manufacturer shall be the transformer shall be approximately at ambient temperature, and no temperature correction applied to the result. The result may be affected by a remnant magnetism, which is caused by some of the measurement. One of these is winding resistance, and also another test is impulse testing. The impulse test also affect the no load loss and are usually higher after such tests. Usual practice is to over-excite the unit for a short period, let's say 5-10 minutes, to eliminate this residual magnetism before we actually perform this no load loss measurement. Similarly to the load loss, we would normally expect no load loss to agree with design values and results from sister units. The no load loss and current should respect the specification and the guaranteed values. Also, IEC 76 part 1 allows tolerance of 15% of no load loss and 10% of the total loss. But again, most of the clients, they specify their own limits, and if they are not respected, if they are not met, then penalties apply. So in the next slide, we will be talking about the performance and temperature rise test in particular. Temperature rise test is a type test, and the procedures for determination of temperature and temperature rise values during factory testing, they are described in IEC 76 part 1 as part 2, item 7. The purpose of the test is to check the thermal performance of the transformer at steady state condition. If the transformer have more than one value of the rated power, for example, more than one cooling mode, the temperature rise should be performed for each rated power. If agreed, the temperature rise test could be guaranteed and performed for a specific lost cycle operation or overloading condition. Details for these are listed in part 7 of IEC 76 part 2. The limits for top oil temperature rise, mean winding rise, and winding hotspot are guaranteed values. There is no limit to other special parts like core or tank temperature rise, but the heat generated should not cause damages to the unit or degrade the oil. Some users apply limits for parts which are accessible from ground level for obvious reasons. The temperature rise test method described in IEC 6076 part 2 is the short circuit one, where we have one of the windings energized. In most cases, this is the high voltage winding and the other winding shorted. This is the setup for load loss practically, and the measurement is performed again using measuring transformers and power analyzer. Ambient temperature is measured by sensors placed on specific location around the transformer. Top and bottom oil temperature is measured in dedicated pockets on the top of the cover and radiators inlet and outlet headers. At the beginning of the test, the sum of load loss and no load loss are applied. Once stable condition is established, we can determine oil temperature rise. Then we reduce the current to the rated one for 1 hour, followed by switching off. Then we measure the winding resistance and extrapolate the results to the moment of switching off. Based on the extrapolated resistance, we determine the winding temperature, and we can also determine the hotspot rise based on calculation or from temperatures measured by sensors embedded in the winding. IEC suggests DGA analysis to be performed before and after temperature rise test, especially for large transformers as a fault detection tool. And Annex D of the standards is dedicated to detection of localized overheating based on DGA. Some more details could be found in IEC 61181 also. So on the screen you can see a graph how the top oil temperature would normally look during temperature rise test. At the first moment, we have increasing of the temperature, heating up process, where the top oil temperature rise, and after a moment of stabilization, we reach, let's say, the flat part of the graph, where at the end of which we can obtain the top oil temperature. Here we have a condition of which we need to comply with, and this is 3 hours with difference of the top oil temperature of less than 1 Kelvin per hour. After that, we can reduce to rated current for 1 hour in order to determine the average winding temperature by measuring the winding resistance for a period of, let's say, half an hour. And based on this resistance, to extrapolate to the moment of shutdown, and based on the resistance at the moment of shutdown to obtain the average winding temperature. I would like to show you some examples, practical examples from our real work on the field, where we found some issue. We have a customer which asked us to check his DGA results for 36 shunt reactors, which were relatively new. And the reason was that the customer found the DGA really suspicious. So we insisted also to have a look at the field test results and also the available factory test results. When we review the factory test results and especially the temperature rise test results, we found that the test on the shunt reactor is not performed correctly, and actually no correction was applied to the results because the test was performed at nominal voltage, but especially for shunt reactor, the standard requires the test to be done at maximum voltage. This was not done during the FAT. So we also find that the applied hotspot factor is much lower than what normally IEC 76 part 7 recommend for medium and large power transformers. So based on the raw test results available from the work test certificate, we did our recalculations and we found the hotspot rise significantly exceeding the guaranteed value and possibly causing a hot spot within the winding. So another example, a customer reaches in order to assist with an FAT on a small working transformer, and during the temperature rise test we found that the manufacturer has difficulties to measure the temperature of the oil getting into the cooler, into the radiator correctly. The manufacturer applied a sensor on top of the header instead of using a special or dedicated pocket, which is placing the thermometer inside, in the middle of the oil flow. But at that time, the customer they doesn't have the opportunity for any other measurements or to improve the test setup. And what we found during the measurement is that the temperature measured on the cover in the special dedicated pocket is much higher, or practically the temperature measured on the surface of the cooler inlet is much lower than the temperature on the cover. Usually we expect these two temperatures to be very, very similar, but in this case the difference was more than 10 degrees, and we didn't accept that. So based on our calculations, we found in this case the top oil rise exceeding the guaranteed value, and also the low voltage winding rise also exceeding the guaranteed value. We then reject the transformer and insist improvement in the cooling system. The cooling system was redesigned, and after that we retested the unit successfully. Actually, what the manufacturer did is to install one additional radiator to improve the cooling of the transformer.
So we're just about to enter the last section of today's webinar. So this is going to be your last opportunity to start putting questions in before the end. So yeah, please use the questions tab on the right hand side of your screen in the control panel, and we'll get to the questions at the end. Back to you, Stefan.
The purpose of the dielectric test is to verify the dielectric capabilities of the transformer isolation system. The required dielectric tests and the test voltage level, they depend on the highest voltage for the equipment, or UM. The required tests are summarized in the table displayed, and the classification is made based on the and defines three categories. The first one is up to 72.5 kV, second one from 72.5 to 170 kV, and the last category is above 170 kV. The withstand level for each test should be specified by the customer, and usually it is based on the national practice. The review of the dielectric test will start with impulse tests. Their purpose is to verify the capabilities of the transformer to withstand aperiodic surges associated with lighting strikes and switching operation in service. In addition to lighting impulse, the test voltage may be suddenly collapsed to zero, simulating insulation flashover, and to check the capabilities to withstand high frequency phenomena. The equipment used for the test consists of impulse generator, which charge in parallel and discharge in series to produce the test voltage, capacitive divider for measurement of the test voltage, and sphere gap, which is responsible for chopping of the lighting impulse. The voltage is normally of negative polarity. During switching impulse test, wave shape should particular parameters of the wave shape should be accomplished from time of more than 100 microseconds, time above 90%, higher than 200 microseconds, and time to zero more than 1,000 microseconds. Lower duration of time to zero parameter is allowed in specific designs, and especially for shunt reactors. It could be increased by inducing remnant flux in the core, by applying impulses of opposite polarity at reduced voltage between the test impulses at full test voltage. This is how a real switching impulse oscillogram looks like. The impulse is with negative polarity, and the decrease which you observe after approximately 2 milliseconds, this is caused by saturation of the core. Yeah, this graph, it differs a little bit from the ideal, which use ideal impulse. The general definitions related with impulse test and the requirements to the test circuit are drawn in IEC 60 part 1. Some test circuits, in some test circuits, oscillations may occur at the peak of the impulse called overshoot, and if it is relatively high to the test voltage, then the testing is not that effective. IEC 60 part 1 introduced a special factor, K factor, in order to filter the high frequency noise and obtain the test voltage more accurately. But there is some concerns how appropriate is this K factor for transformer testing. This is how an ideal lighting impulse looks like. The standard specified virtual front time of 1.2 microseconds with tolerance of plus minus 30% and time to half 50 microseconds plus minus 20%. When neutral terminal is tested, the front time could be extended to 13 microseconds. Chopped wave lighting impulse should have time to chopping between 3 and 6 microseconds, but in some cases, chopping time between 2 and 3 cases may be accepted. This is how real lighting and chopped waves looks like. Again, they are of negative polarity, and the full wave presented on top is not very good. and this is because of the high overshoot. And some correction of the test setup were needed in this case in order to improve the wave shape during the tests in the test laboratory. The usual test sequence for full lighting impulse consists of one reduced or a reference impulse and 3 full test voltage impulses. In case chopped wave is required, then the sequence differ a little bit, but it consists of one reduced shot followed by one full, 2 chopped wave, and the sequence completes with 2 full waves. The test sequence for switching impulse test consists of one reduced wave followed by 3 full test voltage waves. To minimize the effect of core saturation, usual practice is to apply impulses with reduced polarity, reduced voltage and opposite polarity in between the test shots. The test, it is helpful to achieve time to zero parameters mainly, but this technique also increase the time to zero parameter. The tap position is chosen in a way that the test voltage for the winding with lower UM is as close as possible to the corresponding test value, if any. The criteria for successful testing includes absence of sudden collapse of the test voltage, or if there is no significant difference between the voltage and current impulses recorded at reference and full test voltage. Operation of protective devices like Buchholz relay or strange noises are indication for a fault also, and sometimes failure may not be detected based on the transients to oscillogram, and success of the impulse test is thus confirmed through the applied voltage and induced voltage test, which are following the impulse testing. Here again an example from the real field, test field. On the left rectangle, you can see voltage on top and current oscillograms at reduced test voltage. And on the right side of your screen, the subsequent voltage and current oscillogram at 100% test voltage. You can see on the right side there is significant difference in both current and voltages compared with the reference value, and this is because a failure occur. So this is how an oscillogram indicating a problem would look like. This is, let's say, a good case in order to demonstrate a problem, but in other case, the failures are not that visible on the oscillogram, and a very careful look in this diagram should be taken. So this is how the problem looked like after the transformer was taken out of the tank and the windings were disassembled. We found a multiple failure location within a particular area of the winding, and it was believed that the failure is caused by mechanical damage during assembly. The next test we will review, this is the applied voltage test. The purpose of the test is to check the main insulation of the transformer, and the voltage source for this test is usually dedicating, regulating, and step-up transformers. Manufacturers sometimes use a resonance test system for this test as well. The voltage is measured by voltage divider and a peak voltmeter. Each winding is tested in series. Duration of the test is 60 seconds, and the test frequency should be higher than 80% of the rated frequency. The test is successful if there is no collapse of the test voltage. This is how a dedicated resonant test system looks like. The source consists of two stages, 250 kV each one, and a voltage divider. The peak voltmeter is not presented on that picture because it is located into the test room. The induced voltage test is the last dielectric test. It is the most important and probably the most stressful test for the dielectric system. It produces temporary overvoltage at a few different voltage levels, as described in IC 76 part 3, item 11. The voltage source for this test is usually a test generator or static converter at frequency higher than the rated one to avoid core saturation. Typically, test frequency between 150 and 400 Hz is used for that purpose. The test voltage is applied to the low voltage winding and measured at the low voltage side again using voltage transformer and power analyzer. Here we measure the peak voltage divided to the root square 2, and also we measure the RMS at the same time. As a test voltage, we take the lower value of these two. This is how the test sequence of induced voltage test with partial discharge measurements looks like. The first part of the measurement is measurement of the best ground level, which is performed at 0.4 of the multiplied by the rated voltage. It should be less than 50 picocoulombs. After that, it's increased to 1.2 rated voltage for a short period in order to obtain a stable reading of the picocoulombs, and then increase to 1.58 multiplied by a rated voltage for 5 minutes, where we also obtain the partial discharge level. After that, we go to the stress level, 1.8 rated voltage, and the duration of the stress level depends on the test sequence. No limit in terms of partial discharge is defined for this level. If the transformer passed successfully the enhancement level, the voltage is reduced to 1.58 rated voltage for 1 hour, where we measure the partial discharges for every 5 minutes. The limit here is 250 picocoulombs. And if that's successful, then we reduce the voltage to 1.2 rated voltage to obtain the partial discharge level again, and followed by a new measurement, a repeat measurement of the background level. The good laboratories would have a background noise level of less than 15-20 picocoulombs. As I already noted, partial discharge are monitored using the test tap of the capacitive graded HV bushings as a coupling capacitors. Partial discharge are important indicator for design and quality problems of the insulation system, including contaminations, poor quality materials, sharp edges, or issues with the oil impregnation. Sometimes it requires time to develop partial discharge activity, so the duration of the test is relatively long, with an enhancement level of a very high voltage. The partial discharge system is calibrated before use on each terminal. In case elevated PD levels are detected, further investigation is planned or should be planned to localize the problem, as different technique might be used. Suitable technique for this purpose are UHF probe and also acoustic partial discharge measurement. And one more example from our practice in the field, we have a single phase HVDC transformer, which during IVPD test indicated a problem at 570 kV but the test voltage, it was 630. We were not able to reach that level because we exhibit a collapse of the voltage at 570 kV, and then the manufacturer decided to stop the test because of this failure. And the investigation of this problem continue with another PD measurement, acoustic one, with some sensors located at different places on the tank in order to find where the source of the PD is. This is where we found the PD activity within the main, within the active part. We were able to locate it, which made the failure investigation further much easier. Following the localization of the PD activity, the transformer active part was taken out of the tank, and we performed an inspection. We found the faulty area. Actually, there were two places indicative for a problem. One was very close to the core, and the other was related with the high voltage winding. And there was no other fault areas within the active part found. This correlated very well with the location indicated by the acoustic measuring system. Unfortunately, we were not able to to identify the reason for the problem in details. The manufacturer suspect that some contaminations in that area caused the problem and the breakdown, actually. We believe that this definitely is not a design issue, because this was one of the last of totally 12 transformers of the same design tested, and all of them passed the test successfully. The winding was rebuilt, and the transformer was then retested again. It passed all the tests successfully. So why the FAT witnessing is that important? As I mentioned previously in the presentation, this is the factory testing are the last quality assurance check before the unit leave the factory. So the main purpose is to identify if there is a defect related with the design or manufacturing or the assembly. Also to ensure the unit complies with what we specify, because it's much easier to, if this is identified at that stage, to be corrected in the factory. It's much more cost effective and prevent losing a large amount of time for transportation as well. Yeah, and installation and commissioning and decommissioning after that. Critical items where the attention and skills and knowledge of the inspector should be focused. This is the measuring equipment. It is very important, the equipment which is used during this test, to be calibrated, and also the equipment should be suitable for the test we performed, and with the appropriate accuracy class. Test procedures, or how the tests are performed. This is maybe the most critical part of the FAT. This is something we observed in very details. This should agree with the standards, with the applicable standards and specification, and there should be no shortcuts taken during the testing. Yeah. So practically during FAT, the manufacturer provides the final results, but it's critical to be sure that the test itself is performed in the correct way as per the correct standard. Also, evaluation of the test result is very important. The result should comply with the design data, should comply also with guaranteed value and acceptance criteria. In case we found a significant deviation in this data, this is an indication there is some defects, most likely during production. So as I already mentioned, it's important to find all the problems within the factory when the unit is in the factory, because in some cases, just taking the transformer out of the site is very, very complicated and cost ineffective. So in this case, we have a platform here, and the transformer fell just after a couple of years and needed to be replaced. So the process of taking the transformer out and replacing it with a new one is it's a very, very difficult one, and related with a lot of problems. In relation with the factory acceptance test and how they should be performed, what to look like during this test, we prepared a dedicated ebook which could be found on our website www.dovo.com/FAT. So if you are interested, you can have a look at the website, and you can download this short guidance for free. So this is generally what I wanted to present you today. So I am ready for some questions if you have any.
We have questions, don't panic. I do thoroughly recommend the ebook. Stefan is the author of it, and it is a really good informative guide and shows the value in many ways. And as some of the examples he was showing in the presentation, that investing up front with good factory witnessing to prevent problems once units get into service and further down the line is a money well spent. So I'll run through these in order, Stefan. So you have to throw your mind back to right back at the very, very beginning of the webinar. So someone has asked, and this is a more generic question, but what's the main benefits of a 5-limb transformer, and what is the best mesh/control measure to fit onto the end limbs?
The purpose of this, first of all, these 5-limb transformer, they are mainly associated with a big transformer, big powerful step-up transformer mainly, and the purpose of this test is to reduce mainly the no load loss, because I already said during the presentation that the no load loss, they are presented in the transformer since we energize it. They practically don't depend on the load. If we have let's say 10% or 100% load on the transformer, the no-load loss are practically the same. So if we want to, if we have a big transformer, so a big power transformer, and we want to reduce the, let's say, the losses, we want to reduce the losses caused by the no-load loss, we can invest a little bit more money in a 5-limb transformer. Reduce practically the losses and have a bit more efficient transformer.
Okay, and the is this the best mesh / control? But I'm guessing he's talking about stress control on onto the end limbs.
Sorry, Simon, I'm not sure I understand.
Yeah, I'm not sure either. Okay, we'll skip. We
can keep this question, and I will review and
exactly.
What
I should say to everybody is anybody who has asked a question, we will follow up with you afterwards just to make sure that we've given you a good, thorough answer. The same person actually asked, what are the main challenges with core through bolts?
With core through bolts, the main challenges are actually related with the insulation of these core through bolts and keeping them, how to say, tight, because the insulation in this part of the active part is very critical. We should be sure that these bolts are well insulated from the rest of the core, practically, because otherwise they might produce circulating currents and localized overheating into the core. So insulation of the core through bolts is very important. Also, the core through bolts, they keep the core lamination very close to each other, so reduce the vibrations which are produced in the core. So it is also very important to be tight correctly, let's say, and keep them tight during the service of the transformer.
I think before I ask what I would add to that is we certainly had issues in the UK with circulating currents through the core through bolts, and for some designs it's been possible to cut a hole in the side of the tank to repair and replace the through bolts. So one thing maybe to think about is when the transformer is being designed, make sure the bolt is in a place that you can potentially in the future get to it from the outside, so that if there is an issue, it can be fixed.
Yeah, what I would like to add in this to this question is that there are much more modern designs which don't use these core through bolts, but instead of they use a special, let's say, a bar or strap which is going along the window and keeping the lamination tight, practically doing the same job as the core through bolts.
Okay, next one. A couple of questions here, and it's relating to, obviously, somebody's buying a lot of transformers because they're talking about 90 units. But they were saying,
that's a big number.
Yeah. So how often would you witness a temperature rise test and also noise measurements? So that they're talking about sampling rate, but I think what they mean is how many units out of 90 would you actually test?
So temperature rise test and noise level measurement, they are type tests. And in case we have one design, it should be done just on, let's say, the first sample in order to confirm the compliance of the design. However, in case of such a big series of transformer, and especially if they are critical units, I would suggest to repeat the type test on every, let's say, 10 units to check the consistency of the design, to check also the manufacturing. The noise level measurement, it is a very practical measurement to identify some issues related with the core, because during operation the core is producing noise due to vibration, which is causing a higher noise. So in case we locate a unit with higher than normal noise, we can find a problem related with the manufacturing. So yeah, I would recommend for such a huge group of units, let's say every 10 units, to be sample, or let's say perform these two type tests on, let's say, 10 units, every 10 units.
I think, as you said as well, it gives you confidence that there's consistency in the manufacture as well. So I think that's an important point.
And also it is important, the rating of the transformer as well.
Yes. Next question. Oh, hang on, I've got out of sequence here. Any recommendations for the sequence of the tests?
Actually, IEC 76 part 3, it recommends the sequence for the dielectric tests. And generally the sequence ends with induced voltage test with partial discharge. This is particularly important because it can give some indication for a problem arise during the impulse tests. It's not all the time, or let's say 100% sure, that you will be able to find a problem based on the comparison of the oscillograms which happen during impulse tests. But I would say that completing the sequence with partial discharge measurement, induced voltage test with partial discharge level measurement, will give you, let's say, confirmation that there is no particular problem with the dielectric system, and you have a unit with which is fit for service. I definitely don't recommend you to perform any dielectric test following the partial discharge measurement.
Okay.
There is no special, let's say, sequence for the performance tests. You can do them whenever you want. They are not stressful for the insulation. The sequence is more critical for the insulation system.
Okay, thank you. We've still got quite a few questions, so you probably have to have short answers for the next few.
Yeah.
Can you please explain the demagnetization with 110% rated voltage?
Yeah, the purpose of this thing is when we increase the voltage to, let's say, 110, 120%, to get rid of the DC component, which is practically causing the magnetization or orientation of the domains in the core in particular way. So that's clearly the purpose. When we have overexcitation for a period of 5-10 minutes, we practically get rid of this component, the DC component, and then it's time to measure the no load loss in particular.
Okay. Somebody's asking about special tests. when should a customer consider the requirement for special tests, such as lightning impulse or switching impulse? Conversely, when shouldn't they be requested?
This depends very much on the rating of the transformer and the purpose you are using the transformer. But I would recommend to request some special tests like SFRA. It is very simple test and can give you an indication for a problem related with the transportation. Because this test was performed in the factory, we can easily reproduce on site before energizing. And in case there was some displacement of the windings or any other damages, mechanical damages which arise during the transportation, we can easily identify, let's say, by this test. We can create a very, very good reference point for the commissioning test and also for site assessment tests. This is a test which I definitely recommend you to perform.
I think another way of answering the question would be to say, think about the test before you've ordered the transformer, which I know is maybe a slightly facetious answer, but we see this with customers some of the time where they have written their specification, they have ordered their transformer, and then they are trying to effectively change the design by adding additional testing in. And that's certainly where some customers would run into problems. So think ahead is probably a different way of answering the same question. Sorry, we'll just quickly move on. Pumps running during dielectric tests, question mark.
I'm not sure what the problem is, what the purpose, what the idea of this question is. Maybe there is a special test, let's say, of let's say doing some sort of no load energization for some short time with pumps running, but generally the purpose of which I mentioned in the presentation for the pumps running during the test is to equalize the top and bottom temperature, especially for loss measurement.
Yes, I suppose, and potentially, I guess if you're doing a PD measurement, you don't want the pumps running because they could increase the noise level.
It will create a noisy environment, so it's not preferable.
So whilst we're talking about PD, a couple of questions related to PD. What's the rejection level for a PD measurement? So I guess what's the pass-fail criteria? And related to that is, can you pause the PD measurement and then continue again? So I guess they mean take the voltage down, do something, and then take the voltage back up again.
No, I definitely would not recommend you to pause the measurement and continue again. I would, in case there is some issues noted during the measurement, either with a high background noise level or some PD activity which is not coming from the transformer, or even if it's with the transformer, if the manufacturer decide to interrupt the test even for a short period, I would clearly recommend you to start from the beginning. Simon, there was one more question, I think, related with the PD, and this was the rejection level. So IEC 76 Part 3, it defines the rejection level, and for a voltage level of 1.58 rated voltage, the 1 hour level, the rejection level is 250 PC. For the following level is 1.2, and there the rejection level is 100 PC. So also very important thing is to observe the behavior of this PD level over the 1 hour period. It's a long period, and we can check the behavior of the PD. It's very important after this enhancement level to have a moment where the PD levels actually decrease. And during the 1 hour period, we shouldn't see increasing trend. Increasing trend, especially for the last 20 minutes, it's a bad indication and something which it's point to, let's say, reject the unit.
Okay.
It is also defined in the standard that the unit could be rejected if we observed increasing level of PD in the last 20 minutes.
So a couple of questions related to failures. Is it possible the distribution transformer less than 2 MVA can fail under the induced voltage test with a PD measurement? During induced voltage with PD measurement, sorry.
During induced voltage test, every transformer can fail. I think this is the most stressful test for the insulation, and I've seen various transformers failing this test. Partial discharge measurement on this transformer is very interesting because the distribution transformers are usually very small, 10 or up to maximum 33 kV. So partial discharge measurement is not mandatory for them. It's I think it's not that easy to do the measurement.
Okay.
Because you need an additional coupling capacitor. It could be done, but you need an additional coupling capacitor for each phase.
Okay. So I suspect the next person has had a problem, which is why they're asking this particular question. So in the event that a test is failed, for example, apply voltage, but the supply carries out repairs, how confident can we be in the long-term fitness for service if the test is passed when repeated?
So in such situation, I would recommend a close investigation of the untanking process and also close following of the failure investigation and the root cause analysis. It depends very much what the problem is, which parts are involved. Also, following a rebuild, let's say the transformer is subject to repeat at least the dielectric test. So if it passed successfully, we should be, let's say, confident in the quality of the dielectric system, because we are talking about the dielectric issue, obviously related with applied voltage test. So if the unit passed successfully the repeat testing, then we should be confident with the quality of the insulation system. But I will repeat that we need to follow very, very closely with the manufacturer the root cause analysis and the inspection after taking the active part out of the tank, and to monitor what the problem is in order to decide how we will go ahead with this unit.
Thank you. Two last questions. One is going to test your deep knowledge of standards. So you may not know the answer to this one off the top of your head. There's a large variation in between the IEEE and IEC regarding noise level definitions. Which one gives the better end result?
Yeah,
you can always say we'll get back to you on that one, because you may need to actually refer.
The answer of this question wouldn't be that simple, and I think it will take some time to answer that one. I don't think we have that time at the moment. Yeah, we will get back to this person later after the presentation.
Okay, I think that one's probably yes. And then the last question, any recommendations for must-do tests on site? So before you answer that, what I would say is we have had one or two people ask us about running a webinar on site commissioning tests. So it's possible that we will next year actually have a webinar on that. So look out for that on the Doble website or our events page. Any thoughts on that one, Stefan?
Yeah, it depends what the purpose of the testing actually is. Is it a fault? Are you looking to check for a fault, or this is just a regular condition assessment or commissioning of the unit? So if it's just a regular condition assessment, I would recommend transformer ratio, let's say winding resistance, and important for the insulation system, this is capacitance and tan delta measurement. Also magnetizing current to check the for possible short circuit and problems related with the core winding resistance. I think I already said that.
DGA.
SFRA.
DGA.
It's a good tools for to check for some deformations, winding movement, problems with the core as well. And if we have the result from the FAT to compare, then it's even better. DGA, as you said, that's a very, very useful tool if we are looking for a problem within the unit, and I would definitely recommend to take regular samples in order to catch any incipient fault activity within the transformer. DGA is a brilliant tool for detection of fault.
Yes, and I think your comment about
your
comment about SFRA at the factory and then on site is also very valid, because again, we have seen issues where transformers have been dropped, had collisions or whatever in transit, and things have moved, and the SFRA is a very powerful technique for checking for that kind of in transport damage, as well as then obviously all the electrical tests that are done.
Yeah, that's true. That's true. Yeah, in particular cases, we might decide any other tests which could be done on site, but as I said, it depends on the case.
Okay, so we're over on time now. We've had a lot of questions, which I think is absolutely fantastic. So Stefan, I'd like to thank you for all your hard work pulling that together today. Everybody, just as a reminder, you will get a link to be able to the webinar, so you'll be able to play it back at your convenience. If anybody does want to listen to the first part of this two-part webinar series, so that was around specifications, design reviews, which comes obviously before the transformer is built and inspected. Please reach out to Stefan. You can see his email address there, and he can pass that on to me, and I can get you a link to that other webinar if you missed it. If not, thank you for your attendance today. It's the holiday season rapidly approaching, so enjoy your holidays and end of year celebrations. And thank you very much, and hopefully we'll see you on a future webinar.
Thank you very much. Thank you for your attendance. Thank you.